Hello. Today we're going to look at precipitation reactions and use them as an example to illustrate writing molecular, total ionic, and net ionic equations for reactions that occur in aqueous solution. Before we look at the various types of equations, it is important that we understand what a precipitation reaction is. A precipitation reaction is a reaction between two aqueous solutions that results in the formation of a solid and a new aqueous solution. In the example on your screen, we are reacting aqueous potassium iodide with aqueous lead 2 nitrate. You'll notice in the center frame, when the two solutions are mixed, a yellow solid begins to appear. That yellow solid is lead 2 iodide. The aqueous solution formed above the solid is potassium nitrate. How did I know that this solid was lead 2 iodide? It turns out that there are a list of solubility rules that tell me which ionic compounds are aqueous, in other words, will dissolve in water or are soluble in water, and which ionic compounds are insoluble or will form solid precipitates when placed in water. Your textbook has a table of solubility rules very similar to the one you see on the screen in front of you. It is not necessary to memorize that set of solubility rules in terms of an examination, as it will be provided. However, you must be able to interpret the rules in order for them to be useful on an exam. Interpreting these rules is not the focus of this video. So we're going to proceed assuming that you understand how to interpret these rules. However, if you have questions about interpreting solubility rules, be sure to contact your instructor or consult your textbook. If you look at the rules in front of you, you will locate the rule that says chloride, bromide, and iodide containing compounds are generally considered soluble. However, you will note there's an exception to that rule, which includes compounds that contain lead 2+. This is why in our previous example, lead 2 iodide was the solid. Ions are compounds containing K+, potassium ions, and NO3- nitrate ions are soluble, and that is why we are certain that the new aqueous solution formed was potassium nitrate. Let's look at a different example to illustrate how to use precipitation reactions to write molecular, total ionic, and net ionic equations. The precipitation reaction on your screen is the reaction between silver nitrate of an aqueous variety, potassium chloride, which is also aqueous, to form solid silver chloride, and potassium nitrate, again, which is aqueous. If you study this reaction carefully, you will notice that the K+ and the Ag+ tend to switch partners as they react. By that I mean, notice that the silver plus ions in the reactant side are combined with the nitrate ions, but on the product side are combined with the chloride ions. In a similar fashion, notice that on the reactant side, the chloride ions are combined with the potassium ions, but on the product side, the chloride ions are combined with the silver ions to form solid silver chloride. There's a swapping of partners in terms of ions that occurs in precipitation reactions. That general pattern applies to all precipitation reactions. The molecular equation lists the reactants and the products in their molecular form. It looks very much like the equation you see on the screen in front of you. A couple of notes. Notice that the equation is balanced. Notice that each reactant and each product clearly has a state, solid, liquid, gas, or aqueous, associated with it. In the case of precipitation reactions, the two reactants are aqueous. Notice that of the products, we have one aqueous solution and one solid. To know which substance is aqueous or which substance is a solid, you must consult the solubility rules referenced previously. A molecular equation does not paint an accurate picture of what is actually occurring within an aqueous solution. Within an aqueous solution, things that are soluble actually split up into their ions. This is why a total ionic equation might be a better way to look at all species involved in a precipitation reaction. In the total ionic equation, all strong electrolytes, which includes strong acids, strong bases, and soluble ionic salts or ionic compounds, are dissociated into their ions. Insoluble ionic compounds, weak acids and bases, gases, and liquids do not dissociate into their ions. Our focus in this example, because we are discussing precipitation reactions, is limited to soluble and insoluble ionic compounds. The total ionic equation more accurately reflects the species that are found in a reaction mixture. The reaction of silver nitrate with potassium chloride has the total ionic equation shown on the screen. Note that we have a single silver ion plus a single nitrate ion plus a single potassium ion plus a single chloride ion, all aqueous in our reactants. In our products, note that because silver chloride is a solid, it does not separate, but potassium nitrate is aqueous and it does separate into K+, more potassium ions, and NO3-, the nitrate ions. As you study the total ionic equation, you likely will see ions that appear in both the reactants and products in the same form. For example, there's a K+ ion on the reactant side and a K+ ion on the product side. If you cross out all of the species that appear in the same form in both the reactants and the products, what remains is referred to as the net ionic equation. In the case of the reaction of silver nitrate with potassium chloride, the net ionic equation is Ag+ plus Cl-, both aqueous, yields AgCl solid. The net ionic equation represents the reaction you actually witness when you mix these two solutions. The ions that you cross out in the total ionic equation are referred to as spectator ions. These are ions that came to witness the show but not participate. These are ions that are found in the solutions above the precipitate. They're very much like spectators at a sporting event. They came to watch the game, they did not come to play. You can apply this process to any precipitation reaction or any other reaction that occurs between two aqueous solutions. It's probably important that we summarize the process. First, write a balanced molecular equation. Remember, a balanced molecular equation clearly illustrates the state, solid, liquid, gas, or aqueous of each reactant product. It also ensures that the law of conservation of mass is not violated. Second, dissociate all strong electrolytes in your molecular equation into their ions to construct the total ionic equation. Third, cross out anything that remains unchanged from the left side or reactant side to the right side or product side of the equation. Finally, rewrite the equation maintaining or keeping the species that are not crossed out on either side of the equation to generate the net ionic equation for the reaction. Your textbook provides a lot of practice in this particular issue. This is a topic that a lot of students who cannot accurately write the names and formulas of compounds tend to struggle with. The only way to get better is to complete more practice.